All right, are you ready?
Yeah.
Okay, cool. Hello, everyone. Welcome to our anomaly detection for scientific discovery seminar again. So following our machine learning focused talks, today we'll be starting our scientific application talks. So as the first talk, we're so very happy to have Professor Ashley Villar, and she will tell us about the anomaly detection applications in cosmic explosion. Um, so Actually, she currently is an assistant professor of astronomy and astrophysics in the Institute for Computational and Data Science, co-hire at Penn State. And she got her PhD in astronomy and astrophysics from Harvard. She was also a postdoc at Columbia University. Her research uses the observations of cosmic transient phenomena to study the death of stars. So thanks for joining us, Ashley. Please take it away.
Yeah, thanks so much for having me. Let me figure out my series of disclaimers from the beginning. First is that I'm assuming a somewhat mixed audience. In this talk, I assume more machine learning knowledge than astrophysical knowledge. I'll very much go through the basics of the data and problems we're thinking about scientifically. And then also, the talk is very much a pitch for machine learning practitioners. There are really fun anomaly detection problems that are happening now, and they'll be increasingly more exciting. And so please feel free to reach out if you are interested in some of these and want to collaborate. I think those are all of my caveats for today. Oh, and the last one, interrupt me please throughout with questions. I really, really enjoy having questions throughout. Great, let's get started. Okay, so, oopsie. So I'll begin by introducing very broadly the scientific domain that I think about, and then we'll dive into the details of what type of anomaly problems we're trying to solve. And so I start with this comically sad low resolution GIF that's supposed to be displaying the variability of our night sky. And it may or may not be surprising to you that the cosmos is actually variable on extremely human timescales. We have, there's a comment, but I assume it's okay. We have, so my specific field is called time domain astrophysics, and it literally is studies of the cosmos evolving in a matter of hours to weeks. In particular, what I think about a lot are the explosions of massive stars. Those are called core collapse supernovae. And they're really fun for a number of high energy physical reasons. They tell us a lot about stellar evolution. All of the heavy elements of the cosmos essentially come from bellies of stars, and the cosmos gets enriched with these elements through these explosions. So there's lots and lots of physical reasons to be excited about this. Because really, we're talking about machine learning, though, I'm going to get in the little bit of the nitty gritty about what our data actually looks like and why it looks like the way it does. And so what happens is in the cosmos, we look at galaxies other than our own, like this pretty edge-on spiral, and we look for new stars in the sky, like you can see here with the saturation spike. And when a supernova goes off, it actually can outshine the entire brightness of its host galaxy for about a month. And what we do is we take new pictures of a patch of sky, compare it to an old picture, and then just literally look for new stars that appear, and we associate these likely with exciting transient phenomenon like supernovae. If I use the word transient sometimes and supernova sometimes, totally interchangeable for the sake of this talk. Transients are just the broader class of things that could explode in the universe. Okay, so this is really the raw data. It is a time series of images, but very rarely do we ever work with these because many reasons. We reduce these into essentially, we concentrate our efforts on this point of light and we reduce our efforts onto it. And one thing that ideally, if I wanted to understand the underlying physics of a supernova coming from this point of light, I want to know what every single photon at every single wavelength at every point in time is up to. And to do that, I would create this type of GIF where I would take a spectrum as frequently as I could so that I could watch the evolution of the bulk properties, so kind of the overall shape of this curve, and the emission and absorption lines by certain elements within either the star before it erupted or new elements that got synthesized in the supernova itself. That's what these wiggles represent. Both are really important components to understanding the larger physical picture of what happened. Where the physical picture, I think of it's kind of three ingredients. We are concerned about what high energy physics is actually powering this event, as in, is it radioactive decay of elements? Is it shock high energy photons coming from some interaction? The second thing that we care about is what type of star actually exploded, and did it have a buddy with it? It wasn't a binary system. And then the third thing we care about is what was the immediate environment like where it exploded. And these are all, if I had every piece of information, in theory I could kind of untangle these. However, it's very, very expensive to get one of these spectra, and it's really easy to think about why. I'm taking all of these photons, I'm making lots of little buckets that they can fall into, which are sorted by wavelength, and so it's going to be a really long time to get enough photons in this tiny blue bucket to have enough signal to noise to do my science. And so the thing that we do is we just make our buckets bigger. In other words, we take what we call photometry, which has broadband filters, so it can be the entirety of these blue photons, and it's much cheaper to get high signal to noise. And then we make time series with those measurements, and that's what I'm showing here, and this is called a light curve. So our hope is that most of the physics is captured in this much cheaper data product known as a light curve, and we will see examples of that soon. However, I want to point out that supernovae are traditionally classified, as in a guess of what the underlying physics is, by spectroscopy. So the assumption is that to get a true label, we have to get a spectrum. And I like to highlight that this is a really hard classification problem for kind of two reasons. The first is that it's very much a hierarchical scheme of labels. And so it's also very historic, so ignore why they are called this. But we ask questions like, do we see signatures of hydrogen in a spectrum, yes or no? And then from there, we ask questions like, oh, well, do I see helium within that spectrum, yes or no? So it kind of naturally has this hierarchical structure to it. But then the second complication is that it's also not as if physics enjoys discrete buckets necessarily. A lot of these are just likely continuous classes that we somewhat arbitrarily decide are more like one or the other. But it's a mix. Sometimes it truly is different underlying physics. And so that also really complicates our picture. But the labels that we use are spectroscopic, so they rely on data that is high fidelity, inexpensive, and they are observational, so they're highly correlated to the underlying physics, but not necessarily exactly one-to-one. So I said that the light curves, luckily, also encode a lot of this physics, which is the case. So although we're looking at the specific elements, because those elements are so closely tied to underlying physics, there are other ways that physics can propagate through our observables. They directly affect the bulk properties of what's happening. And that's why we largely are able to also see that same physics represented in the lower resolution time series that we grab called light curves. And this is obviously a cartoon, but this is always what we're going to be looking at. Some form of a luminosity, just whatever units it appears in, it's a brightness versus time. And we'll be looking at different colors, and they will have just these basic shapes. And we'll use those to guess the underlying physics or to look for new physics. This is a real light curve. I know it's a type 1A because we have a spectrum, and they look a lot worse than my cartoon. So this is, let me tell you a few things about it. This is just a measurement of brightness. Ignore the fact it's flipped. This is brighter, this is dimmer. This is time. The different colors represents where I'm putting my bucket. or the center of the broadband filter. So you can think of, this isn't quite right, but think of the red being like red photons versus green being green photons. Importantly, all of these functions are from the same underlying spectral energy distribution. So the same function that's evolving as a function of wavelength and time, but we have a very sparse look at it. We also have a very noisy look at it. We tend to have fairly significant error bars on these. And really importantly, I think what makes this problem fun is that our light curves tend to be irregularly sampled. So that means both in time, I'm not observing it every single day, but also you'll notice in filter color. So I observe these green photons maybe twice over 10 days and then never again, whereas the yellow photons, I have a little bit of a better cadence. So we have to figure out ways of representing this data that can handle the fact that we are so irregular and sparse and noisy. Was there a question?
Not yet.
Okay, great. Oopsie. So that's our data. That's our underlying physics. Loosely what we're doing, but we'll get more into why anomalies are so fun in a moment. First, I want to point out the fact that we can really start looking for really rare things, which is fun. So this is just a simple plot that's showing as a function of discovery year how many supernovae we are discovering per year. Ignore these boxes, just look at the light blue. And the key point here is that our discovery rate has been growing exponentially for the last few decades, starting with just a dozen in the 80s, and now we find about 10,000 per year. So we're really hitting kind of this marker of big data, which is exciting for the field. But what's more exciting is that in a few years, a new survey is coming online that's being conducted by something called the Villar Observatory. So it's going to start this 10-year survey of the southern sky, where it will observe the same points on that sky every few days. And it's going to be just an absolute game changer for our field. It will produce something like, I think it's 20 terabytes of raw data every single night that we need to start digging through. And I should say this, that the namesake is Villar, who famously discovered dark matter, so excellent title for it. But turning to our focus, so the science of supernovae, how does this affect the plot that we just saw? And so I dorkishly turned it from a logarithmic scale to a linear scale to make it more dramatic, but it really is dramatic. So this is our previous plot. And the Villar Observatory breaks exponential discovery growth for us. It's a huge transition for our field. So we are going to go from 10,000 supernovae every year to well over a million every year. And what is exciting or scary, depending on how you want to see it, is that I mentioned earlier that our entire classification scheme is based on spectroscopy, or the high-resolution, expensive measurements. Well, this black line is showing you, as a function of time, which of these events received at least one spectrum, so had a classification associated with it. So right now, we're not doing great. We get about less than 10% of all of the supernovae that we discover every year get a classification. And to be honest, we basically throw out 90%. That's just the state of the field right now. When Villar comes online, there's just not going to be a dramatic increase in spectroscopy. It's really expensive, and that would be hard to have a dedicated instrument to do so. So imagine that within a factor of 2, that's not changing. The fraction now of things which get followed up is quite bad. Only 0.1 of all supernovae will have a traditional label on them. Or a different way of saying this, which is how in this cartoonish picture again, is we have this needle in a needle stack almost problem. We have millions of supernovae every year from LSST that are sitting in this data every night. We have, let's be really generous, like thousands get one label, so we at least have a label on them. But then, because these phenomena are transient, we have to actively make a decision to spend telescope time and expertise, so people hours, studying these events. And realistically, this is a guess, but maybe 100 or so can actually receive the dedication they need to fully understand the physical picture behind them. So I'm just repeating fractions over and over, but I really want to emphasize this point that 100 in a million is like a 1 in 10,000 level of importance to the field. So it's literally as if my entire field had to come together, decide, okay, in 2020, we can only publish on one thing. What will we pick? That's the level of importance for driving the field forward that we have to decide upon in real time, because we don't get a second chance with these. And so it's really important that we have some objective function to figure that out. And my objective function, and I think what people here are interested in, is really thinking about what do we not know about? So certainly there is something that is an unknown in the cosmos, some set of high energy physics, an environment of the supernova or the type of star that explodes, that set of ingredients that we're just not expecting. And so I'm really interested in anomaly detection for figuring out what is this 1 in 10,000 level of thing we should follow up in real time. On the right-hand side, I'm showing, oh, I feel terrible. I didn't cite it. This is from Dan Perley et al. From a recent survey, the Zwicky Transient facility, where these really are observational breakdowns of the type of supernovae that we know. So it's similar to that cartoon tree we saw before, but now it's actual pie charts. One thing to note is that the universe doesn't create physics equally. Our classes are clearly not balanced, which is another fun part of our challenge for classification, although we're not talking about that here. But one thing I like to highlight is that if we go really deep, I don't think I actually show this, I don't. For even the most rare type of event we know about, so the one I highlight is, we're all the way down here, superluminous supernova. If you propagate, just multiply up this fraction, it represents about 1% of the entire population that we know about. It's one of the most absolutely rare events, and it's very much a needle by today's standards. Lots of follow-up time is dedicated to understanding these really weird events. You can ask me about the physics if you want, but I think what's fun, though, is that LSST is going to find 10,000 of these things every single year, and we currently have a sample of maybe 100 of them, and that's over the entire time we've known about their existence. And so the things that we consider rare and exciting in needles today are absolutely not in that category for tomorrow. So to me, it really makes sense to be thinking about what else could be out there that we can't even currently write down a physical model for. Are there any questions on the scientific background? Otherwise, I'm going to jump into some solutions that we've been thinking about. Nope. Okie doke. Then let's talk about ML. And I somewhat assume people are familiar with these things, so stop me if you're not. That's totally fine. So we use. We're going to try our best with these irregularly sampled light curves to build some latent space that can help us look for anomalies. That's really what it comes down to. And to do that, obviously, these are going to be data-driven methods. In particular, I want to point out the fact that I mentioned I wanted to be physics agnostic, because what if I cannot write down the model? So for these data-driven methods, I just like to give credit where it's due, that there are really fun data sets we can play with right now. The real data sets cover all of the wonderful systematics that we expect in the real cosmos. So there's lots of important tests we can run here. However, they're very small. I point out just the Pan-STARRS Medium Deep Survey is only 5,000 supernovae in total. So it's not even close. It's like literally less than a week of LSST data. There are simulated sets. The one I love to highlight is Plastic, which was this amazing community effort led by Rick Kessler, Renee Holtchek, Gautam Narayan. That actually was a Kaggle competition. And it was this effort to bring to literally ask the community, give us all of the models we can think of, and we will, as realistically as possible, simulate it. And so this is a much larger data set that, although it still doesn't have the full diversity we expect, it by definition does not have unknown unknowns. It's very useful in testing a lot of these, and it's totally open source, really great resource. Okay, so what I'm going to talk about for anomaly detection in particular is well, here I say classification, but we're going to use it for anomaly detection. It's a semi-supervised classification method. We're going to use the unsupervised part, obviously, for this, where we're going to build a latent space, specifically with a recurrent neuron-based autoencoder. There's an additional adjective. It's also variational, which I just typically don't point out, but it's helpful to have a probabilistic encoding. So I assume probably everyone here does know what an autoencoder is, but I can say it anyways. So especially because I heard that you had a ML review. An autoencoder is simply a type of architecture of a neural network. I'll say it in the way that I say it to physicists, because I think it's a fun analogy where I try to convince physicists that it's similar to just us fitting a model, where it might take a very long time for me to write down the equations, but as soon as I write down the equation for how a supernova evolves, I only have 3 free parameters. I can only change the mass, the energy, and how much nickel or how much radioactive material it produced. That's it. And so I compare a neural network to doing the same sort of dimensionality reduction that we are doing, where it's spending most of its effort training these weights. But then once we fix everything in test time, we only have a small number, in this cartoon 10, free parameters, which must exactly describe our multi-wavelength, multivariate, irregularly sampled light curves. And actually, the way we do this has a little bit of bells and whistles. I think I mentioned recurrent. Let's not talk about that. I guess we can. One of the bells and whistles is that when we get to our encoding layer, all of these neurons are actually recurrent. And one of the things that we do is that at the encoding layer, we append a time value. So it's almost like calling a function at different times. And so I return the flux estimates that I'm interested in different wavelengths at different times, which allows us to do interpolation and extrapolation of our observable, which is a light curve, directly from our latent space. The recurrent neurons are really helpful for our problem. The reason why is because we do get our data live every night. We get a few more observations from LSST, or we will, and those can again be in kind of an arbitrary set of filters. And what's helpful about this is that every night we can get improved, hopefully, representation in our latent space to make predictions for what it should be doing in the future, but then also to be using that latent space intrinsically to make decisions about whether or not we should be triggering our active follow-up. So I like to show people this in action in particular. So the points with the large error bars are showing you this is real data. I know it's a type 1a because we got a spectrum. This data really only has one high signal to noise data point. That's this guy. Again, you can see it's in different filters, so different colors of photons. And the lines are actually representing the output of our autoencoder, which, because we're appending different times to this encoded space, we can call it at any time we want. I'm able to really nicely interpolate and extrapolate what it thinks this light curve will do. And so with one point, it actually does a bad job. I'll just tell you as an expert, that looks nothing like a type 1a. But as soon as we get just a few more days of data, it does a much better job. In particular, it's hitting roughly what I expect the luminosity to be. And then I'll go ahead one more. And then eventually, what's nice is it's not a perfect representation, but it gets even some secondary characteristics that are unique to this type of supernova. So things like an extra bump, if you will, in the redder bands, which in this case are I and Z, or the yellow and purple colors. So that seems good. It seems like our latent space is able to recreate the general properties of a light curve. And so we've been using this a lot for classification tasks. Basically, our goal, this is why it was semi-supervised. In an unsupervised method, we train this autoencoder, we get a latent space. It just generically learns what a supernova looks like. We then convert all of our mismatched sizes, different sparsity levels. We translate all of them into a latent space with this variational autoencoder, and then we use really standard methods like random forest to do classification in this latent space. Let's see how we're doing on time. No, we're really good. Okay. So I'm going to skip that and just point out the fact that this is really what the group cares about. We use the same architecture, probably in the way that you can expect, to look for needles. And I want to be super clear that we use pretty simplistic methods for anomaly detection, and we use this entirely for out-of-distribution anomaly detection methods. And we can talk more about why that distinction is important. There's a question. Yeah.
Did you use, since large curves of the plastic data is extremely sparse, especially for wide phase deep region, did you use any interpolation method before you gave the large curves to autoencoder?
Yeah, I love that question. So we absolutely did, and I skipped over that. So we use a Gaussian process method to do interpolations over time and wavelength. So it's a two-dimensional kernel that we're training, and it's just a really simple squared exponential kernel. And so we use that to pre-process, and in training our neural network, we don't require that the time sampling is even, but we do require that for every point in time, there is some estimate in every filter. So in this case, like there has to be some estimate in G, R, I, and Z. And if that isn't the case, we use the Gaussian process to give us a best guess at the mean within that filter and the uncertainty. And so the neural net sees a time relative to max. It sees best guesses for the photometry, and then it sees uncertainties for that photometry at every point in time.
Thank you. I want to ask any other question. And which kernel did you use? I read your article, and I see that you used a Gaussian kernel during the interpolation.
Yeah, we did.
I'm also trying to address the sparsity, but it's really, I'm working with 14 classes, and it's really difficult to address decide the kernel. Why didn't you use Gibbs or metrin kernels?
Yes, that's a really good question. I love it. So we used, so I'll be a little careful, I guess. In the anomaly detection paper, we actually switched it up. And we had a custom kernel that instead looked for correlation overlap within the filters, but the squared exponential or the Gaussian kernel is easier to explain why this happened. So in our case, the physical modeling is actually, there are pretty nice approximations where literally if I want to write down the physics of this, it's essentially just like a Gaussian low-pass filter on some input physical function, like a power law or an exponential decay. And so because of that, very naturally, there really is this singular time scale that is relevant to our physics. And so a squared exponential is actually, it just happens to be a pretty nice guess. There are some caveats to what I'm saying. There's some classes where that's not as good of an approximation, and you can see that our Gaussian process does not do as well of a job. Actually, I don't think I'll mention this, but I'll just make a broad statement of, you're absolutely right, though, that the kernel is, it's forcing a prior, in a sense, of information on my neural network. I am strongly making assumption that there is only one relevant physical timescale by doing this, and that is not the case for a lot of other events. One that I think about somewhat are supermassive black holes can be variable, and they very much are not described by a Gaussian kernel. They're described much more by a damped random walk type of kernel.
Thank
I
you
hope
so
that answers the
much.
question. Yeah. It's a complicated answer, sorry, but yeah. Any other questions? I forgot where I was. Okay. Yeah, excellent. So like I said, we can take this exact same architecture, which is just it's a variational recurrent autoencoder, just a variational autoencoder. That's all that matters. So we are taking every light curve, condensing it into a single-sized vector, and then we just do really easy methods to look for anomalies. I'm sure you could do better here. We'll talk about ways you could do better. So in this study, we just did an isolation forest, where I don't even think I describe how it works, but I can. It's very straightforward. An isolation forest just makes a series of simple cuts in your learned latent space. So here I'm just showing a subset of 2 dimensions, although I think it is a 10-dimensional space in our case. We make a series of, they're actually random cuts, and an isolation forest keeps track of how many cuts it takes for you to become isolated from the large-scale population. And then it trains many trees with these random cuts, and it keeps track of them, how many cuts this guy took in tree 1, 2, 3, and then tries to understand some average of that. And by doing this, we, in a sense, are keeping track of an anomaly or a weirdness score for each of these events, where the intuition is that if I make a cut here, I've isolated these 2 immediately. Whereas if I want to isolate someone deep within my cluster, it's much, much harder. And so the number of cuts it takes is inversely related to your anomaly score that comes out of an isolation forest. And I want to point out here that in this plot, to be really clear, each of these points represents an individual supernova, and we trained a variational autoencoder, which one of the key points of this is that we attempt to enforce that the clustering of these supernovae will look as much as possible like a Gaussian normal distribution. And we can see that some of them don't fit into that mold, which is great. That means that in this space, they stand out as anomalies. So I will point out that I didn't include this because it might not make sense to a non-astrophysical audience, but we did this study on that large-scale plastic simulation of LSST, and then we did compare, because that was a simulation, we had all of our meta labels, we knew exactly what physics was put in, and we did in fact test to see that the anomalies which come out, where anomaly was top 1% of the most anomalous scores, it did in fact pick out the more rare classes that were injected into the simulation. So that was that was really great. I will point out now for a specific event. So I mentioned this guy already, a superluminous supernova. This is one of the rarest ones in our data set, but we expect something even weirder to show up in LSST, but this is the best we can do, basically. So this is its light curve. And then this plot is showing how do the different latent features, and with some arbitrary scaling, how do they kind of evolve with time? And you can see that loosely they start to converge pretty quickly. And then in particular, I keep track on colors of just when does this anomaly score reach the top 1% of the weirdest looking objects that the autoencoder or the isolation forest has seen. And what's really great for astronomers is the fact that our anomaly detection algorithm, as simple as it is, picks up something as being anomalous way before it reaches peak light. And there's a few reasons why we care about that, but the key one is to just remember that we are humans making decisions in real time to trigger active follow-up. And so the earlier, the better. Peak time is especially kind of key cornerstone point where we really want to be well before that. And then this is just a simple visualization in that latent space of what's kind of happening here, where the black represents a sample of all the supernovae, and the purple, it represents this particular weird object, where the darker color represents later and later in time. So you can imagine this guy's kind of walking out of the main distribution as it evolves and becomes increasingly anomalous. And I want to point out the fact that we trained this anomaly detection algorithm on a fairly small fraction of the full data set. So the full data set contains about 1 million supernovae, but we only used about 10,000 to train this, which is really like, or was it, maybe it was 100,000, but less than a month of LSST time. We would almost immediately have enough information to pick out at least this level of rarity, the 1% level of anomalies. We also did, I lovingly refer to this as the ugliest plot I've ever made, so I will walk you through it. We did some sanity checks to try to understand which ones were correctly being pointed out as anomalies and which ones were incorrectly being pointed out as anomalies, where again, we can only ask this supervised-ish type of question because it's a simulation and so we knew the answer. The left-hand plot is showing you a vector plot of how is the anomaly score changing on average as a function of time. The background is showing a histogram of how many points do we even have in a light curve at this time relative to maximum. So in other words, a lot of our light curves only contain a few points, and so almost by definition, they are near maximum because they're the only ones we've seen. And that kind of makes sense because most of the supernovae we look at are right at the dimness level where we can't see anything, and so they just kind of peek their head above that for a little bit. So that's why we see this clustering here. But the key point is that the anomaly score seems to largely totally flatten right before peak. And so this score that we're deriving, or a different way of saying it, is the encoded version of the light curve in our latent space doesn't seem to be moving very much as soon as it reaches peak. So that's great because it seems like we are somewhat confident in what we think the light curve will look like as it evolves. This is really the ugly guy. What it's showing is things which are in blue, light and dark, ignore the variation in color. Well, let me say a different way, I'm sorry. All of these events that are colored, whether they be in blue or orange, were at some point in our algorithm highlighted in the top 1% of the most anomalous things in the sample. The blue were actually minority class events. We knew the physics was relatively rare. The orange were things in the majority class. They are definitely not anomalies. Typically what they are the metadata is wrong. It's just, the metadata is wrong and they purposely simulated it to be wrong. Specifically the distance. So we have some estimate of how far away these things are, and it really impacts our understanding of what they can be. And so some of these just have they call it a catastrophic failure in that estimate of the distance, but it is a simulated to be as realistic as possible catastrophic failure. So this should happen with LSST. So that's typically why the majority class gets labeled as anomaly. Like it looks way too bright or something for what it is. Luckily though, most of the anomalies which get flagged and are actually things of the minority class happen before peak. And for whatever reason, things of the majority class do not get highlighted until post-peak. So this is great news for us because it means that very likely these misclassifications in a sense, so not anomalous or normal events, would be flagged too late, that we likely wouldn't spend additional follow-up time on them anyways, because in a sense we've missed our window. So that was really helpful. Okay, so I'm gonna stop there And once again, see if there's any questions now on this like particular solution that I've introduced to the problem. And the rest of this talk is highlighting some really fun just domain-specific problems that we have for any practitioners in the audience that are thinking about, who want a new problem to work on, basically. Okay, I don't think there are any questions. Okay, so increasingly, this is what I've been thinking about, is really understanding how our domain knowledge and the methodologies we're developing can talk to one another in order to create the most informed solution to some of these problems. So I'm not the first one. I thought of this and then immediately realized there was a very recent review, so I'm not the only one to think about this. But there's kind of 3 locations that I've been thinking about where to input some of the physical knowledge, or places that I think the frontier can be pushed. And I'll talk about different examples in our field where we're doing this, whether that be the model, the data, or the objective function. So I want to point out something I very briefly mentioned, which is the fact, again, that our data has, by definition, it has majority-minority classes, it has common physics and rare physics. And what we are most interested in is understanding the rare physics, or at least what I'm most interested in. So some of the things that we do commonly is to actually, input this information into the data. A different way to say this is that we're giving our neural net an implicit prior on what our data should look like. In particular, we have one class that makes up type 1As that make up 70% of everything. And so if I just call everything a type 1A, I'm already doing pretty well. And so we make sure to reflect this information, and in particular, in the variational autoencoder I just showed you, it correctly, if given no other data, you just have one data point, it will assume it is type 1A-ish most of the time. And that's really helpful because then it will not stand. It's very unlikely to stand out as an anomalous event, given just for the lack of data and not because it's actually interesting. This is also a very common way of kind of having some less of a prior, but more of like a regularization to, let's see, be equivariant to some symmetries within your data sets. So the easiest example is you might have a rotational symmetry. In other words, if I rotate a galaxy, it's still a galaxy. We have more interesting symmetries that do exist. In particular, there's a super strange cosmological interplay between how far away you are and how red your light is. And so that is one symmetry that we can very much write down easily, but it really hasn't been formally integrated into a lot of our methodologies. One way people are doing this is just directly by bolstering our data by putting things at different distances. But it hasn't entirely been used in its full capacity. So in the second place, I think about inputting some of our physical intuition is in the objective function or the cost function, whatever we want to call it. And so for the methodology I showed, well, for the anomaly detection, when we are training things like the autoencoder, we use really standard just a weighted mean squared error, where we're weighted by an uncertainty that we, like we just said, we get from a Gaussian process. And we can use, I don't use this, but if we wanted to, we could use things like class scaling so that we could reward it more for getting the rare classes correct if we wanted to. But one thing I've pointed out now twice with several cartoons is the fact that our physics is naturally hierarchical. There are subclasses of different types of underlying physics, and that has not been integrated into our cost functions yet in the literature. This is something I'm thinking about right now, where I think just it's not, I don't know, knock on wood, I don't think it's so hard, but probably the most difficult is just making sure that we think about this correctly as a graph structure, and then making sure we're able to write down an adjacency matrix so that we can efficiently compute an objective function that has a hierarchical cost. And then we can also, and this is now a little bit of a deep dive. Okay, it's a little bit of a deep dive. I've been talking a lot about totally physics agnostic approaches to this problem, but we can also, in the cost, have some regularization that is physically motivated. So again, one of these can just be, you can include a regularization of symmetries that you want to conserve in your cost function. So for example, you could ensure that if you were doing an autoencoder to recreate galaxies, you could somehow make sure that a rotational symmetry was satisfied within your cost function. In this case, this is a really different approach. This is also a different type of transient. I apologize. This is a recent work I did with a wonderful student, Jiwon Park, about something called active galactic nuclei, which is when a supermassive black hole is interacting with a local disk. In particular, it's accreting. And so this is the main point, is that we see a light curve like this, that unlike our supernova friends, it doesn't have a transient increase, decrease in light. Instead, we see variations throughout a longer period of time. And so one thing we were interested in doing was specifically trying to understand, can we create an autoencoder-like scheme or representation learning that can simultaneously do a reconstruction on the light curve and have a prediction for the physical parameters of this AGN. And so I'm not going to go into details. This is not an autoencoder exactly. It's a Bayesian attentive neural process. But for the sake of this talk, it's fine. We don't need to know the difference. It's a largely unsupervised, I guess semi-supervised method, where the key point is that our cost function just has two factors to it. One is that it will be rewarded for correctly giving us back the same light curve, so reconstruction, just like in a normal autoencoder, but then at the same time using that encoding space to correctly predict some physical parameters about the AGN. And so this is an example of the outcome of that, where on the left-hand side we have a reconstruction of, this is very much a toy model of LSST data. Now on the right-hand side you can see posteriors, it's a Bayesian solution, posteriors of some of the key physical parameters that we might care about for an AGN. Things like, how massive is the supermassive black hole? How far away is it, which is what a redshift is. And then luminosity, which has to do with the accretion rate. But the key point here, again, is that we have been exploring adding these rigorously as regularization terms to the cost function to have much more interpretable latent spaces that we're learning about that can more directly be used for science. And one way of thinking about this is that it's much easier to potentially look for anomalies in our physically motivated latent space because we have a good domain intuition of what is weird physics in that space versus a completely uninterpretable latent space. And finally, I just want to highlight that the last node of our triangle is enforcing our physics within the architectures itself. And this is kind of a really simple way, again, of doing this, where in this case we were looking for really anomalous, not transients, but variable stars that had periodic light curves. And so one very easy way to enforce a periodic condition in a convolutional neural net is just to give it periodic boundary conditions, which is exactly what we did. And we found that this was in fact helpful in creating a latent space that was more robust to the periodic nature of these events. And I will point out that we did successfully, from a catalog of thousands of light curves from variable stars, we were able to pick out, with again just an autoencoder plus isolation forest setup, really interesting evolved stars that exist very much in their own locus in an observational phase space, even though we were really using latent spaces from our neural network to select these things. And then I just want to highlight that there are so many fun questions that still remain open. This field's undergoing a massive big data revolution where we will start to have probabilistic guesses on underlying physics. We'll have to start addressing the fact that we need to find unknown unknowns or anomalies without any spectroscopic information and pretty low resolution data sets. And we also, something I didn't touch upon is we have mixed format data sets. So I've been talking all about these light curves, but we start with, as I said, we start with images. And we don't really capitalize on all of the information we have available to help us look for weirdos or anomaly detections, even though we know that weirdos like to live in weird places. So it's very much, again, an unexplored subdomain. Okay, I think I will leave it here for now, and I think I do have time for questions. Thanks.
I thank actually for the great talk, and if you have questions, you can unmute yourself. Okay, I think I have a few questions. The first thing is that I think for the autoencoder application, like you had actually, it's not image inputs, right? They're actually the light curve inputs.
That's right. Yeah, so like I said, so it doesn't see the image whatsoever. It's already been reduced into, you can think of it like we just integrated the light in a few pixels of the image. And so the autoencoder sees a time series where we tell it the time of the observation and the different fluxes and the different filters or the colors, and then we tell it the uncertainties on those.
And do you have relevant works on if you have the images directly as inputs, because you also talk about the data augmentation on image sets?
So that's a really good question. We do not use image time series, although that will be available, I believe, with LSST. So there's kind of two reasons why. I don't know if there's two reasons. There's one large reason, which is the fact, so it's be a lot more compute time to work with those images, but most of our physics really is condensed to just that small area on the image because only a small amount of that image is actually changing. However, like I said, supernovae know where they were born, and so the types and the rarity of physics is very much correlated to the underlying galaxy. So we don't have time series of images, but definitely singular images, I am positive, are exceptionally important in solving some of these problems.
Okay. Yeah. The other thing is that right now, I think there was a question from the audience. Maybe you can ask first, and then I will follow with my question. So it's Eric?
Yes, hi there. Hi, Ashley. Near the end of your talk, you had an AGN with much more data than you get for your supernova number. And your posterior misses most of the small time scale structure. Yes. So I was wondering, could you combine a parametric ARMA model that's designed for the short memory behaviors with your machine learning and give a combination parametric machine learning analysis and capture all the phenomena?
Yes, we should absolutely talk about this because we definitely can. So the way, I didn't explain this at all, the way this works is it thinks of the problem as a set of pairs. So it doesn't even think of a time series. It just thinks that X's and Y's know that they're paired in some way. It learns a representation for how those pairings happen. And then it tries to make a light curve this way. And you've exactly picked up on some of the issues that it hasn't truly learned the correct, how do I want to say this? The correct underlying autocorrelation functions that exist. And so, yeah, absolutely. Being able to integrate some of the more common models like karma models for this would be wonderful.
I think there is a question from the chat. It's from Sabon. And would you like to ask yourself, or I can read it for you? All right, I'll read it for you. So it says, can you please explain how you're taking of the rotations and how you compensate for that within a model?
Oh, how would one actually do this?
I think it's a rotations. I think it's a data augmentation.
So yeah, I think so. To this person's credit, I think I did make an offhanded comment that one could include this in the cost function. It's true though. In the slide I showed, I just mean in data augmentation, you can augment your data set by, and this is really common, just by doing rotations or by doing zoom ins or something. And the idea is that by showing your neural network more examples which have the same classification or something, it becomes more resistant to these sorts of symmetries you expect. However, one could also imagine putting this into a cost function where, for example, you can check to see that the output of the, I get some encoding, then the decoding of that, if I were to flip the image, you could enforce that the flipped image would have a very similar encoding in that space. That's a harder solution to the problem.
The follow-up question is that what about an incorporation of groups, like a Klein 4 group?
Yeah, okay, so I don't know anything about group theory, but group invariant neural networks do exactly this, and I can't answer intelligent questions about them, but I know that there are solutions, and you want to look for group invariant neural nets.
All right. Any other questions? Feel free to unmute yourself.
Yeah, I have kind of a philosophical question, more than a technical one. But I'm working on an anomaly detection project in a completely different field. But one thing that's always really hard to do is to say, how good is this? Like, because you're finding something different, right? And sometimes, maybe the answer is like, okay, well, we'll publish it, and then 10 years later, a paper will come out on this super juicy thing that we found. But I wonder, is there any way that you can, with the anomalies you're finding, are there any kind of ulterior heuristics that you can use to say, this is probably something really interesting versus you showed a great example in simulation, but if you didn't have the simulated thing, is there a ranking?
Yeah, I really love this question, and I do not have a good answer. One thing that people have been looking at is active learning with these anomaly detection algorithms. So just have a panel of experts that feed back into your neural net. However, of course, in our case, I will say I do have some expertise of looking at low resolution data and could imagine an active learning in that case. But for some of this, we unfortunately are just going to have to waste resources and trigger on the wrong things. And then on the opposite end of the spectrum for your question, I we'll never know if we picked out the correct weirdest things, and that's really concerning for me.
Is there an active learning setup maybe with the triggering? You trigger, you get more information, you say, oh, actually that was boring.
Yeah.
And then feed that back. I guess that'll sort of naturally happen.
So that will definitely, yeah, exactly. So that will naturally happen, and that is what we're imagining. It's just expensive. It's expensive to get the answer wrong for us. And there's no such, we won't have the ability to change the rate of our time series or something if something looks like it is interesting. So we want higher resolution. This public data set, we won't have control of that, if that answers your question.
Oh, could you work with some other external telescope that is tied into your algorithm and it points the telescope and collects, could you have a loop like that, or is that just not realistic in this field, or
No, we can, yeah. And it's a consideration for sure.
Yeah, for sure. It's expensive. Yeah. Thanks.
But if other fields also, I assume that the other domains have the same issue, which I'm so glad you brought up, is that there really is no great objective function for anomaly detection, and it's an issue.
Yeah, I don't know if there's I don't know if there's really an answer that works everywhere, but I'm just interested to hear what it's like in your field and maybe get some ideas of how it is in mine. Yeah. Well, thanks for that.
Yeah.
Any other questions? All right, if we don't have any other questions, I think Ashley has to go because she has another meeting afterwards. So let's thank Ashley again for the great talk, and see you later again.
Yeah, thank you so much.